teams. So you are one step away of making it among the top three winners for Envision of Future 2021. You should be very proud, and we are really excited to hear your pitch. So you will have exactly 15 minutes to go and pitch your project, and then it will be followed by questions from Steve, Todd, and Robert Winter from Dell Technology. So feel free to start whenever you are. The floor is yours.
I think we're ready, but we have one missing member. So
That's safe.
we have one missing member.
Remember. Okay, Pierre, are you ready?
Okay, we're ready.
Okay, good luck.
Okay.
Good evening. We are a team from the Faculty of Engineering at Ain Shams University in Egypt, and we present a brain wheel, a brain-controlled smart electric wheelchair. The team members are Iman Mohammed, Michael Magdi, Mustafa Ashraf, Fancy Yasser, Pierre Nabil, and me, Bara Magdi. This project is supervised by Dr. Saif Dawlat. Firstly, we will start with a brief introduction to clarify the project's motivation. Why did we choose this project, and what is its importance as a practical product?
The main problem we aim to solve is that more than 780 million people around the world, including 6.5 million people in Egypt, suffer from some sort of disability that prevents them from normally moving around. These people are in a constant need of a wheelchair. The issue is this wheelchair will be either a traditional wheelchair, so the user will have to move it manually or have a caretaker constantly pushing it, or a better alternative, an electric wheelchair. So all the user has to move it is to control a joystick to move around. The problem is that a lot of disabled people aren't even able to move their hands, so they won't be able to control anything. That's why our aim was to develop a wheelchair prototype which the user is able to control without having to move a single body muscle. This is done through a brain-computer interface, as we're about to see in more detail.
The main idea of our project is based on the steady-state visually evoked potential signals, or SSVEP signals, which are the natural response of the brain to visual stimulation at specific frequencies. When the eye retina is excited by a visual stimulus in a certain frequency range, the brain generates electrical activity at the same frequency of the visual stimulus. These brain waves are what control our wheelchair's movement. So our project is an electric wheelchair prototype that the user can use by wearing a headset that reads their brain waves. In front of the user, there is an assistive screen that displays flashing buttons, each corresponding to a control command that the wheelchair can take. So for example, forward, left or right, etc. All the user needs to do is look at the desired button or command, and the wheelchair will move accordingly. Meanwhile, the wheelchair is simultaneously checking for collisions. If any imminent collision is detected, the wheelchair will ignore any control commands that would cause the collision and only allow the safe commands. The wheelchair also supports a simplified autonomous mode that allows the user to select from certain predefined locations a destination to which the wheelchair will autonomously move to as a self-driving vehicle. It also has a safety feature that automatically sends an SMS message to a designated caretaker in case of an emergency. All this is achieved by 4 main modules. The first module is the Brain-Computer Interface, or BCI, responsible for determining the user's desired command. So it takes its input as raw brain waves from the headset. These signals are then processed and passed to a machine learning model for classification, which outputs the desired control command. The module is also responsible for the user interface displayed on the assistive screen. The second module is the computer vision, responsible for continuously detecting collisions in front of the wheelchair. This is done using an object detection model paired with a depth map obtained from a stereo camera. So it takes its input as raw image from a stereo camera and outputs a Boolean value representing whether there's an obstacle in front of the wheelchair or not. These two modules pass their outputs to an embedded system responsible for all the hardware of the project, the power supply of the motors and the electronic components, and the interfacing of these components, and is obviously responsible for the wheelchair's motorized motion according to the received commands. Finally, we have the motion planning module, which is responsible for the autonomous mode of the wheelchair, from determining the long-term path to the short-term behaviors and decisions.
What makes Brainwheel a special project? Brainwheel is special as it uses brain-computer interface to offer a solution for a difficult problem. With Brainwheel, we achieved 98% accuracy on real-time predictions of our PCI system, which is comparable to the state-of-the-art models. Brainwheel also has an autonomous mode, which is used to facilitate long-distance trips and also to prevent eye strain by eliminating the need for constant eye contact with the screen for long periods of time. Regarding the safety features of Brainwheel, we have a collision avoidance system and an emergency SMS message sent in case of system faults. Brainwheel interfere many technologies and approaches in one project. For example, brain-computer interface, computer vision, machine learning, signal processing, embedded systems, motion planning, all working homogeneously together. And finally, we are targeting to publish a research paper.
Now, we'll start talking about the performance indicators used during the project period, starting from KRA, Key Responsibility Area. KRA refers to the different areas of responsibility for each module. KPI, Key Performance Indicators, that are derived from KRA. The main KPIs we followed are performance metric of the control command's predictions accuracy. The current PCI accuracy is 98% and we want to achieve it 100%. Quality standards, we followed some manufacturing standards such as software standards like functionality, reliability, usability, maintainability, portability. For example, we developed a PCI tool. This is the software package that we developed. It's responsible for offline recording of the brain signals, the training of the machine learning model, and real-time prediction. The tool followed all applicable software engineering standards. Third, time measurements. The current real-time PCI decision takes 5 seconds and we plan to reduce the time response. Finally, cost measurements. We will now start making some comparisons between different wheelchairs in terms of prices. The normal wheelchair price range is $100 to $150. The electric wheelchair price range is $700 to $1,200. Our brain wheelchair prototype range is $2,200 to $2,500. However, estimation of our wheelchair cost after optimization, according to some cost optimization principle, is $1,000 to $1,500. Thanks.
In this video, we present a short demo showing our project Brainwheel. The first demo shows the manual mode. In this mode, a screen has 4 flashing boxes as shown. When the user looks at one of the 4 flashing boxes, the system registers the command corresponding to the box that the user is looking at, and the wheelchair can execute the requested instruction. In the main view, we can see the wheelchair's movements from a distance. In the screen view, we can see the user looking at the button representing his required instruction on the screen. You can find the required instruction stated under the screen view. This video has been sped up for a better viewing experience. This product can help its users to move freely in any direction that they want. This can be a life changer for many people, especially people who cannot move their body and have a constant need for a caretaker to move around. If the wheelchair has any software faults, the GSM module sends an SMS to the caretaker to help the user out. Okay, finally, the target location has been reached. In the second demo, we show the obstacle avoidance system of the project, which is one of our wheelchair's safety features. In the beginning, the user gives the system forward commands. The second forward command is interrupted by the obstacle detection system due to detecting a wall in front of the wheelchair. The user keeps giving forward commands. However, the wheelchair doesn't execute any instruction that will cause it to hit an obstacle. When the user changes his command to a right command, the wheelchair can execute it because it will not cause a collision. In the third demo, we show the autonomous mode of the wheelchair. In this demo, we show that no one is sitting on the wheelchair to demonstrate that the wheelchair can move fully autonomously without anyone to guide it. The user should select the target location using the BCI GUI, and the motion planning module then uses the GPS module to find the wheelchair's current location. Then, the GSM module sends a request to an online GPS navigation API, which returns the high-level mission plan. The motion planning module then uses the occupancy grid from the computer vision module to plan the route that should be taken and sends instruction to the embedded systems module to move the wheelchair until the target location has been reached. Finally, the target location has been reached. So what's next for our project? First of all, to turn this project into a fully fledged product, we would need to improve some features, such as adding more safety features, like checking the wheelchair is stuck, measuring the battery charge level, and adding other IoT extensions upon other things. We can also improve the motion planning system by using a different GPS API and implementing a better local planner. Finally, we can further optimize the machine learning models for object detection and semantic segmentation for a faster response time. Next, we should start working on reducing the cost of the project. We can do this by developing a simpler headset with 4 sensors only instead of 14. As our tests have shown that we only need 4 specific sensors to get the 98% accuracy gained with all 14 sensors. We can also use a screen instead of a laptop for the GUI, and we can use 2 cameras instead of the Z camera for extracting depth information. Finally, we can integrate the system components into one printed circuit board. The next step is manufacturing multiple instances of the product. The project will be sold as an extension to pre-existing electric wheelchairs. And finally, we can start marketing our project in several hospitals. We can also market for national institutions in Egypt that are interested in the project, such as the National Council for Disability Affairs, the NCDA, or the National Academy of Information Technology for Disabled People, the NAID. Thank you.
Hi team, this is Steve. Congratulations for all your hard work and also for a great presentation. I really enjoyed it, so good job. I wanted to start by asking the team, why did you choose this project? What made you get involved with a project related to wheelchairs?
Okay, so we decided to work on a project related to wheelchairs because we thought it will be, we thought that it will have a large market share. We wanted to make a project that will be helpful for more people.
Okay. The project was really complex with a lot of different modules, hardware systems,
yes,
software systems. So I just wanted to understand how the team worked together on such a complex project. So maybe if I could ask each one of you what you did, and maybe you could answer in the order that you spoke, right? I believe Bara went first and Iman went second, but could you just tell me a little bit about what role each of you played in this project?
Okay. Can I tell you what each person did, or do you want to hear it from each different person?
Each different person, starting with Bara.
Okay, sure.
I was one of PCI sub-team. I worked on GUI and the synchronization between the GUI and the data collection. يعني both should work together, and we have to make them يعني work synchronously.
I was one
Okay, Iman?
I'm Imam Mohammed. I was in a sub-team of embedded system. I was responsible for all hardware in the system, battery and the microcontrollers of, we control the motors of the wheelchair. Also, I was work in motion planning module sub-team.
Thanks. How about you, Michael?
So I was part of the embedded system team, making sure all the hardware was properly set up. I also helped in the integration of the embedded system with the other modules, so the other machine learning models, and make sure that they will all interface properly and work together.
Okay, and Ponce?
Ponce, yes. I was one of the sub-team, the computer vision sub-team members. I worked on the collision avoidance and detection system using two machine learning models, computer object detection and the semantic segmentation model. And that's it.
Okay, and Mustafa?
Hi, I was a part of BCI team member. I was responsible for extracting data from emotive epoch headset and extract the raw data and make a preparation step like signal processing step and make and extract features. Also working on machine learning with my team members.
Okay, and Pierre?
Okay, so finally I was the team leader for this project, and I was mainly working with Ponce with the computer vision module. I mainly focused on extracting depth information and other things from the computer vision module. And I worked with Michael on the motion planning modules.
Okay, was there anybody that I missed, Pierre?
No. We have the BCI team was Barat and Mustafa. The embedded systems team was Iman and Michael. And the computer vision team was me and Ponce. The motion planning module had me and Michael and Iman working together.
So that my next question was going to be, did you have a team leader or did you all make decisions together? And it sounds like Pierre, you were the one that kind of led the project.
Okay, so what we did is I was technically more like a team manager. So we did everything democratically. Like we voted for everything that we wanted to do, and then we executed what we all thought was the best next step for the project.
Well, if you're the manager, then you should give everybody a raise. They all did a great job.
Thank you.
So, Rob, any questions from your end?
Yeah, sure. So again, congratulations on getting this far. Very clever idea. To Steve's point, so you had these 4 modules that you've kind of talked about. Can you explain how you design the interactions between them and how did that communication go with the different teams?
So when we're talking about the integration of all these modules, we designed an interface that would be as simple as possible, so we would be able to meet the hard timing requirements of the wheelchair. It had to have fast response time, so the communication needed to be as simple as possible. So the BCI module had a machine learning model that would take the brain waves from the headset and make a prediction, and that prediction will be sent to the embedded system module. The computer vision module also had to make quick predictions depending whether there's an obstacle or not, and it would also send that that Boolean value to the embedded system module, and then the embedded system would resolve any conflicts, and then just control the wheelchair depending on the commands it received.
Cool. So I guess, from looking at this whole thing, if you're using, the EEG signals, I understand why you're using the screen to generate the signals, but did you find, and I know you said you wanted to go from the 14 to the 4 sensors. I guess my question is there another way that you could look to try to accomplish the same tasks, but completely removing the screen? So could you use just the brain signals to interpret what the user wants to accomplish?
Okay, yes, sure. There are multiple BCI techniques.
Yep.
We researched them all, and we found that the SSVEP technique was the best one in terms of the accuracy that we can gain. So using the screen would be more effective at getting a higher accuracy.
Okay.
There are other techniques, such as the user can just think of a direction, and then we can train the machine learning models to try to find some patterns in the signals. But that will require more than just 4 sensors. The 4 sensors that we were talking about were the 4 sensors pointing at the back of the brain, the part that's responsible for the visual. Yeah, exactly. I just couldn't remember the name.
No, that's all good.
So that's the whole idea.
All right, cool. Yeah, so it makes sense. I was just wondering if there was something else that kind of popped up that could remove that component altogether.
Yeah, there are multiple ideas in the scientific literature, but we thought we'd use the best one in terms of accuracy.
Absolutely. No, it totally makes sense. So one, I also want to give you all for your presentation a lot of credit on, as you were going through it, I was writing down questions. As you kept talking, I kept ticking off my questions because you were answering them already. So
thank you a lot.
Kudos to all of you on that. The other question I had was, so you talked about your market plan of, then, if you did a little bit more work, then you could move to, talking to hospitals and stuff like that.
Yeah.
How are you going to go about getting all of the approvals that you need to even start having those conversations? I know medical devices take years of regulatory compliance and validation and stuff like that. And just by looking at your system, I mean, each one of your modules would have to be validated almost by multiple things, at least in the US, multiple organizations in the United States. So I don't know how it is in Egypt and stuff, but doing that, there would be a lot of things you'd have to step through. Did you all think about how you would start to do that, or what you need to do for this?
Okay, so as far as I personally know, I think that there are not as much regulations on what things that can or cannot go in to be used in hospitals.
Okay.
But there are regulations, but they're not as strict as US, as the US regulations. However, we were thinking about just going and talking to people and managers and seeing what is needed, and we can then try to work on them one by one.
Cool. And then the last question is, as you're doing all of this, and you talked about the GPS, and some features that I thought of right away was a geofence, right, where the certain wheelchairs can go out for certain distances and stuff. And you kind of talked about stuff like that. What about privacy, though? Do you have any concerns for, one, me requesting a wheelchair, or in me plugging on your monitors to monitor my brain, the GPS to track where I go? Is there any concerns around all of that information being collected and being able to be brought together?
Okay. To be honest, we didn't really think about that part because this is just a prototype. So
Yep.
we were going to think about more details about the security features. How can we make the data safe?
Yep.
But yeah, that was part of the next step. Yeah, if we're going to work on that in the future, we would definitely have to think about that.
Awesome. Thank you.
There is also something regarding the data extraction from the emotive epoch headset. It's already encoding, okay, and when we extract in the BCI tool, we decode it again. So so in terms of recording data or reading data during runtime, the data already is encoded.
Okay, so I can restate that a little bit more clearly. So the headset already encodes the data before it sends it to the system. So we have to decode it before we can edit it. So that's a part of the solution.
Yep. No, very cool. That was all the questions I had. Steve, do you have any others?
Yeah. So Mustafa, I know that you had mentioned your KPIs in some of the performance levels, and also Pansa mentioned the 98% accuracy. Help me understand that a little bit more. So 2% of the time, something's not happening, and you want to improve that to 100. So explain to me, what is the gap? What's the problem, and how you're planning on addressing that?
Okay. The problem is during the recording the data, we want to try to use the more accurate signal processing steps, okay, and make data extract at a long time, okay, and extract features more appropriately, and the main and the main point that make accuracy higher. It's here is when we try to make when we try to get when we apply signal processing and it gets a power, okay, the main features of the data set, okay, that is the power corresponding to the specific frequency. So the step will enhance our accuracy. It's by extracting the power features more appropriately and a more enhancing method.
Okay, that makes sense. Last question for me is just wondering if there's anyone else in the world working on this problem or something similar. So at the beginning of the project, did you do a literature search on people working in this area? And if so, did you find anything that was similar?
Yes, sure. We did a research phase at the beginning of the project, and we found a lot of ideas and multiple research papers regarding people trying to work on BCI interfaces with wheelchairs, but they were never this developed. They were only like really simple prototypes of really crude systems working with toy wheelchairs, not even real full wheelchairs. But later, after we were working then further in the project, we found some people that had slightly better versions, but they were not really as developed as we have. We have a lot of extra features that are not in other systems, like the computer vision module having obstacle detection and having an autonomous mode where the user can select a location and just move there. So we have a lot of extra features that are not really found anywhere else. So that's what makes our project special.
Right. And so did you find anybody that was looking at BCI either for wheelchairs or maybe for other purposes?
Yeah, BCI in the medical field is kind of a hot topic in the research field. But as I said, nothing is really fully developed or ready to be sold as a product. They're all just ideas and really basic things, you know.
Great. Well, that's it for me. Great job, team. Thank you so much for a great presentation. I learned a lot.
Yeah,
Yes,
thank you.
thank you.
And we would like to thank you too for this great responsibility, for this great opportunity.
Thank you so much, team, for joining us today. Great job. And we will get back to you with the results and the feedback very soon once all the teams are done with their pitches. So thank you so much.
Thank you.
Thank you.
Okay, thank you a lot.
أنا مش عارف أقفل.